Okay, so we've laid a lot of groundwork for equilibrium systems, and we've talked about how they have a constant that tells us whether they end up mostly to the right or mostly to the left. And now we finally have enough to do some number crunching with it and actually predict what a system's going to do before we get the chemicals out of the cabinet. And let's see how we set one up. They've got a reaction here, and I'm going to write this out big because we're going to build a table around it in a moment. So we have 2-bromine monochloride, and sometimes when those are sitting there, they will decompose, and you'll get chlorine and bromine. Now, we're going to track this system, three different things about this system. We're going to look at what all the initial concentrations are. I'll actually, because it's the first one we've done of these, I'll write out all the words. We're going to keep track of initial amounts, how much of each chemical there is at the very beginning. We're going to keep track of the changes in those amounts, and we're going to look at the equilibrium amounts once the system settles down. Equilibrium. Because these are the three things we track, and they're always, or we normally keep track of them in this order, this is often called an ice table. It's got nothing to do with frozen water, it's just the acronym that you get from initial change in equilibrium. If you hear someone say that C is for consumed and created, that's fine too. Change is maybe a little easier to remember. But we're going to have an entry in each of these spaces for each of these chemical species, most likely. So let's see what they've told us. An amount, they're not saying how much, of bromine monochloride is thrown into a 1 liter vessel. Okay, so we started with some bromine chloride, and they don't mention any chlorine or bromine being in the vessel, so we start with none of those, and we start with, I'll call it X, because I don't really know. So an amount of bromine monochloride, there we go. Nothing else is mentioned being in the vessel, so we're okay saying those are zeros. At a certain temperature, the equilibrium constant is 11.1. That's good to know. We'll put that in our pocket for later. The K for this reaction is 11.1, and the equilibrium mixture contains 4 moles of chlorine. So in the equilibrium row, chlorine is 4. How much is there of everything else? Well, we started with no chlorine, and now we have 4 moles of chlorine, so I think it's safe to say that the change in the chlorine amount was plus 4. We made 4 moles of it. Now that gets us all kinds of stuff. Every time you create a mole of chlorine, according to this reaction, you also create a mole of bromine. These are always created in exactly equal amounts. If you make 75 chlorines, you'll make 75 bromines. So if we made 4 chlorines, there must be 4 bromine also. So we get that number without too much trouble. If there was no bromine before, and we created 4 of it, then there must be 4 at equilibrium. That's not too bad either. How about over here? How much bromine chloride do you think we used up? According to the coefficients, however much chlorine you've got, you use up twice that much bromine chloride. The ratio here is 1 to 2. So whatever number is here, double it, and that gets you the bromine chloride number. So if we created 4 moles of chlorine, we must have used 8 moles of bromine chloride. And if we started with a certain amount of this and then we used up 8 of it, sadly I can't finish this part yet, but we can say 8, x minus 8 at least, just to have some kind of expression for the equilibrium amount. So that's our table all filled in. Now, is there some way we can solve for this x? Or do we need to solve for this x? Let's see, they're asking how many moles of bromine and BrCl are present in the equilibrium mixture. Okay, so we got the bromine. We don't have this yet. Is there a way we could find it? Yes, there is, because we haven't used this equilibrium constant yet, and we can use that to tie these values together. Because we know our equilibrium law for this reaction is K equals, what is it? Chlorine times bromine divided by bromine chloride squared, and that has to come out to 11.1. Well, we know most of these numbers. We know chlorine is 4. Bromine's also 4. Bromine chloride is x minus 8. That's a bit of a nuisance, but whatever. And it's squared, and that's 11.1. So if we write 16 over x minus 8 all squared equals 11.1, you can square root both sides of that. This happens a lot when you're doing equilibrium problems, by the way, so keep this tactic in mind. It's going to come up fairly often. If we square root both sides of this, some good things happen. Well, on the left we have to square root 16, and luckily that comes out to a nice number. It's just 4. When you square root x minus 8, the root and the square cancel each other, so we're just left with x minus 8. That's a bit of an improvement. And on the right side, unfortunately, we have to square root 11.1, and that's not going to be very nice. The square root of 11.1 is 3.33. Okay. Now, to finish this, we can multiply both sides of that by x minus 8. That gets us 4 equals 3.33 times x minus, and 3.33 times 8 is 2.66, I think, or sorry, 26.6. Yeah, 26.64. To finish that, you add 26.64 to each side. You get 3.33x equals 30.64, and then you divide by 3.33. And out comes x must be 9.2, or all of our data has 3 significant digits, so I guess 9.20 would be our x value. X equals 9.20. Now, that's not the answer. 9.20 is the initial amount up here, so that's 9.20. That's nice. But what they're asking for is how much BRCL is present in the equilibrium mixture down here. So what to finish this, you actually have to do 9.20 take away 8, and you get 1.20. That's the value they wanted. So please don't drop your pencil the instant you get an X. Sometimes X is not exactly the thing you want. It's usually means you're making good progress, but it doesn't quite mean you're done. All right, so this isn't the only way we can set up ice tables, and it's not the only way that you can get X's in them. There's a few different ways they can occur, but this is the general idea. You have amount you started with, the amounts that were created or destroyed, or consumed, I should say, and then this is like the total row where you combine the I and C. So here we started with X, we used up 8. There's our new total. On this side, we started with none, we're making 4. Started with none, making 4. There's always one side where you're going down and subtracting, and another side where you're going up and adding. Let's try a couple more. At constant temperature, 0.75 of HBr. Okay, so not too different of a reaction in this case. I'm going to write out a big one because I want to lay out the data underneath it. So 2 hydrogen bromide, equilibrium with hydrogen and bromine. Initial change, equilibrium. And what did they give us? HBr was 0.75 moles. You see the trap here? These amounts are supposed to be concentrations. This is not a concentration. The concentration is number of moles divided by volume. So for HBr, it's 0.75 moles divided by 1.5 liters, 0.5 moles per liter. That's what goes down here. We can do that anytime we want to see if we can catch you, so watch out. These numbers that go in the table are all moles per liter. If you ever see moles, an alarm should go off immediately. HBr decomposes according to this equation. Okay, so they say they put this amount in the container and nothing else, apparently, so no hydrogen, no bromine to start. At equilibrium, the hydrogen was found to be 0.13. This is moles per liter, so that's legit. We can use that number. We don't have to divide it by anything. And they say calculate the value of the equilibrium constant. Well, the equilibrium constant for this reaction is hydrogen times bromine divided by hydrogen bromide squared. We don't have a number for it, but if we could find hydrogen, bromine, and HBr at equilibrium, we could use this. Don't use these numbers. They won't work. This is an equilibrium constant. It's only true when you're at equilibrium, so it's only valid using the numbers in the E row. Don't go putting I or C numbers into this thing. You'll get a result, and it might look credible, but it's not going to be right. Remember, this is KEQ. Well, I often don't write that, but it's important here. Equilibrium constant means it only holds when you're at equilibrium state, meaning we need to find some more stuff in our table. What can we deduce from what we have here? Well, we started with no hydrogen and we ended up with 0.13, so clearly we created 0.13 of it. Hydrogen and bromine are 1-to-1, so if you created 0.13 of hydrogen, you must have created exactly that same amount of bromine. The ratio of hydrogen to HBr is 1-to-2, so however much hydrogen you made, you used up twice that much HBr. If this is 0.13, this must be 0.26. Fair enough. This row, C, is the only one that obeys the coefficients. If you want to think C is also for coefficients in addition to change, that works. So if this is 2-to-1-to-1, you should see a ratio of 2-to-1-to-1 down here also in your change row. Okay, what else can we fill in now? We started with no bromine. We created 0.13 of bromine, so that's our new total. And we started with 0.5 of HBr. We used up 0.26 of HBr, so now we're down to 0.24 of HBr. We just always assume that our reactants are being used up, so it's subtraction on this side, and that we're adding on this side. In this case, that has to be true because we started with no hydrogen and no bromine. You can't go down from there. The only thing that could possibly happen is you go up. You can't have negative amounts of any chemical. So we assume it's down, up, and in this case where the initial number is 0, up is the only thing that makes any kind of sense. So we have our equilibrium numbers now. That's good. That means we can fill in this K. K is the equilibrium concentration of hydrogen, 0.13, times the concentration of bromine, 0.13 again, divided by HBr is 0.24, and we're supposed to square that one. So out come the calculators. 0.24 squared. I'm using my squared key so I don't have to key things in twice. And I get 0.293. Now, yeah, all these data have 3 significant digits, so 0.293 ought to do it for our K. Okay, new thing. 2 carbon dioxides can break down into 2 carbon monoxides and an oxygen. Initial change equilibrium. Okay, what have they given us? 4 moles of CO2, 3 moles of CO, 3 moles of O2 are placed in a 1 liter reaction vessel. So can I just write 4, 3, 3? I hope that bothered you a little bit because these numbers are moles, meaning you shouldn't just blindly put those into a table. However, in this case, those are the correct numbers, and here's why. It's a 1 liter vessel. So what happens when we do our concentrations? The concentration for CO2 is number of moles divided by volume. The number of moles was 4. the volume is 1 liter. 4 divided by 1 is, yes, 4 moles per liter. So it's a nice day when you see a 1 liter vessel. That means you can just take your moles and plop them in here because the concentration and the number of moles will be the same number. This concentration is 4 divided by 1. This concentration is 3 divided by 1. And the oxygen concentration is 3 divided by 1. So nice. Just please diligently check this every time you do an ice table. It's a terrible way to lose points. And if you miss this, these initial numbers are going to be wrong, and everything after that is doomed. You will not recover from having the wrong initial concentrations. So get those right. Okay, so we got that, and those are good. When equilibrium was reached, the vessel contained 4.5 moles of oxygen. Down here we are at 4.5. Okay. What can we figure out from what they've just given us? We got a difference here. We started with 3 moles of oxygen. We end up with 4.5 moles of oxygen. That means net gain of 1.5 moles of oxygen. That much was created. When you create oxygen, you create twice as much carbon monoxide. So if we created 1.5 oxygens, apparently we created 3 carbon monoxides. And when you create oxygen, you create twice that much CO2, so this should be a 3 also. I'm not sure why I wrote 3.0 there. That's unnecessary. Or the simpler way, because these both have coefficients of 2, you can expect these numbers to be exactly the same all the time. So if this is 3, there's a 3 over here also. So what does that tell us about our equilibrium amounts? If we started with 3 moles of carbon monoxide, and then we made another 3, that should bring us up to 6 moles per liter carbon monoxide. And if we started with 4 moles of carbon dioxide, and then used up 3, we should be down to 1. That all good? 3 plus 1.5, total goes here. 3 plus 3, total goes here. 4 minus 3, new total goes there. Now that we have those, they're asking for an equilibrium constant. So what is our equilibrium constant? Should be carbon monoxide squared times oxygen, power of 1, over carbon dioxide, and yeah, that's squared. So do we have all those numbers? I think we do. Carbon monoxide is 6. Remember to square it. Oxygen is 4.5. Carbon dioxide is 1. And we're supposed to square that, I guess, although squaring a 1 doesn't really do anything. So what does that give us? 36 times 4.5 is 36, 72, 144, plus another half, 162. The K for this reaction is 162. Okay, more ice. At a certain temperature, a mixture of hydrogen and iodine is prepared by placing blah-de-blah-de-blah in a 1 liter vessel. Okay, let's get our table organized. They're already pelting us with numbers here, and we need a way to keep them organized, and the ice table does a nice job of that, so let's build one. Hydrogen reacts with iodine to produce 2 hydrogen iodide, and then we have initial amounts, change in amounts, and equilibrium amounts, by which I mean concentrations. And what have they given us? 0.1 moles of hydrogen in a 1 liter flask means the concentration is 0.1 divided by 1. So thank you, whoever wrote this question, for the 1 liter container. Iodine, also 0.1 divided by 1. And if they say we put these 2 things in the flask and that's it, that implies that there is no hydrogen iodide, at least at first. That's an assumption we have to make all the time, and rarely will they spell it out explicitly. You just have to, when they say, I put these 2 things in the flask, you assume that's a complete list and that there isn't anything else. Now, hopefully there's a little more information. When the system reached equilibrium, it was determined that the iodine concentration was down to 0.02. That's our equilibrium iodine. And again, they want the value of the equilibrium constant, which, now let's get it out of the way, HI squared over hydrogen and also iodine. We only know one of those numbers right now, so let's get up to our ice table and start hacking away. What can we find? Anytime you got a column where you know two of the entries, you can probably find the third one. We started with 0.1 of iodine. We ended up with 0.02 of iodine. If you subtract those, you'll find that the difference was 0.08. That much iodine was used up. Hydrogen and iodine are in a 1-to-1 ratio. The coefficients here are both invisible ones, so we use those in equal amounts. And the hydrogen iodide is always twice as much as the others. So if these are 0.08, then this should be 0.16. Okay, now it looks like we should be able to get some totals. If we had 0.1 of hydrogen and we used 0.08, we're down to 0.02. And if we started with no HI and we made 0.16, then incredibly enough, we are at 0.16 for that. Fair enough? Again, we're assuming that the reactants go down and the products go up, and in this case, the products have to go up because you can't get any lower than 0 for a concentration. So the only thing that makes sense is up on the right, down on the left. And let's see what that comes out to. So our HI is 0.16 squared. Down here, our hydrogen is 0.02. And the iodine is also 0.02, so I'm just going to write 0.02 squared. And out come the calculators. 0.16 squared divided by 0.02 squared. And I get that the equilibrium constant is 64. 3 sig digs, 3 sig digs, 3 sig digs. This number has 2 sig digs, but the way we used it, I have to be careful here. This is something we often don't have to worry about, but we may have to here. The initial amount of iodine was 0.100, that's 3 sig digs. The amount at the end was 0.020. So when we subtracted, we get 0.080 for these. This is, before I was being casual about the significant digits, now I'm being careful. Technically, all of these numbers should have 3 decimal places to them. And so the number I used down here in the equilibrium constant actually had, no, it's still 2 sig digs. That was right. So I was thinking maybe this would end up having to be 64.0, but no. The number we put into our equilibrium constant really does only have 2 significant digits, this 2 and the 0 after it. Therefore, this number 64 has 2 sig digs, and that's the correct number. We can stop there.